Hey guys, welcome to Safi Next with another series of videos regarding the application of Schrodinger wave equation. In this series of videos, I would discuss a trivial but very important problem of quantum mechanics. I mean the solution to Schrodinger wave equation for infinite potential well, which is also named as particle in a box and some textbooks. If you search any introductory book on quantum mechanics, you will find this problem as first application of the Schrodinger wave equation. The reason is because this problem provides some very basic concepts. Okay, but here I can give two very strong reasons for understanding the basics of quantum mechanics that compel me to call this problem an important one. And they are: number one, the solution to Schrodinger wave equation for this problem very nicely introduces energy quantization, which is a pure quantum mechanical concept. And number two, the solution very nicely demonstrates the application of Heisenberg uncertainty principle. Other reasons on advanced level that make this problem very important are its application to modern technology in the form of constructing quantum wires and quantum dots. With that said, let me show how is infinite potential well pictorially represented. It looks like this: a bottom line joining two vertical lines, and the arrows on the two vertical lines represents the infinite depth of the well. Similarly, at one side I'm writing infinity, at the other side I am writing infinity, which means that the potential outside the boundary lines is also infinite. The straight bottom line represents that the potential inside the well is a constant, and this constant is numerically equal to 0. The potential function for such a one-dimensional infinite well of width A is mathematically expressed in the form of a conditional function of the form given by this one equation, which says that the potential function inside the well, that is the region bounded by x greater than 0 and x lesser than equals 0, and outside the well it is infinite, that is for x lesser or equal to 0 and x greater or equal to 0 the potential is infinite. Before investigating the quantum mechanical behavior of a particle put inside such an infinite potential well, I would first like to investigate the behavior of the particle from the perspective of classical mechanics. I do this because I feel this strategy will enable us to distinguish between the outputs of classical and quantum mechanical approaches to the problem. So let's do this first classically, and in the next video on this topic I will solve the problem quantum mechanically, and at the end I would then compare the two results, that is the one obtained from the approach of classical mechanics and the one that is obtained from quantum mechanical approaches. So let's go classically. We know that the total energy E of a particle is the sum of its kinetic energy and potential energy, and we write the total energy E in the form of this equation, that is E equals K plus V, where K represents the kinetic energy of the particle and V represents the potential energy of a particle. Since we are dealing with an infinite potential well, and inside an infinite potential well the potential energy we are supposing is 0, so the total energy for a particle of mass A moving with velocity v is simply equal to kinetic energy. That is, equation 1 becomes E equals K plus 0, where 0 I am writing for potential energy, and that in fact equal to half mv square, where m is mass of the particle. And arranging this equation for v, I can write v square equals 2e divided by m, and taking the square root of this equation, I can write v equals square root 2e divided by m. Now equation 2 dictates that inside the well the particle is moving with constant velocity. This constant velocity is possible only when the particle collides elastically with the walls of the well. That is, the particle is losing no energy in collisions with the walls of the well. This further indicates that the particle reverses its direction on each collision. In other words, the particle is oscillating back and forth between the walls with constant speed. Since the acceleration is zero, we can find the period of oscillation by using the equation of motion. That is, the distance covered by the particle is given by the product of velocity and time, and for time I can write this as t equals s divided by v. Since for a round trip s equals 2a and the time taken is time period, therefore writing t equals ta, I can write the equation for time period as ta equals 2a divided by v, and substituting the value of velocity from equation 2, I can further write the time period in the form of energy like this one equation. If we plot the position and velocity of the particle against time, we will get plots like these two. We see in the first plot, since the velocity is uniform, therefore the position is changing uniformly with a straight line from x is equal to 0 to x is equal to a, where x is equal to 0 represents the left wall and x is equal to a represents the right wall of the potential well. While moving from 0 to a, the slope is positive, and moving from a to 0, the slope is downward. However, the period of oscillation and maximum and minimum is same. Subsequently, if we look at the velocity time graph, that is the second one out of these two, the velocity remains constant for straight line and flips its direction exactly at the point of collision with the wall, like at that one position, and the same happens for other ones. So during the motion other than the collision, it is a straight line along time, which shows that velocity is constant or independent of time, and the vertical line that connects the two walls at position x is equal to a and position x equal to 0 represent the flipping of the direction of speed or velocity of the particle. It remains constant between the two walls and flip its direction at the wall from x is equal to a to x is equal to 0 and vice versa. So if we measure the velocity of the particle at any moment, it would either be plus v or minus v. That is, the speed is always constant for the particle. We can also find the average value of position of the particle. To this end, we find the probability of finding the particle between position x and x plus dx, which by definition is given by probability p x plus dx, that is the probability of finding the particle between position x and x plus dx, equals p of x multiplied with d of x. Since the velocity of the particle is constant, therefore this probability, that is p of x, must be a constant, and if I represent that constant with capital C, I can write this side of the equation as c times d of x. Where c is a constant, it must be a constant because of the constant velocity of the particle. In other words, the particle spins equal intervals everywhere within the well. Now, from normalization condition of probability, the total probability of finding the particle over the width of the well must be equal to 1. Therefore, we can write 1 equals integral from 0 to a p of x d of x and substituting the value of p of x, which is c, I can again write it as integral from 0 to a c times d of x, and taking c out of the integral, I can again write this as integral from 0 to a d of x, and applying the integration, I get c times x with limits from 0 to a, which substituting the limits, I can write c into a minus 0, and that of course reduces to c times a, and rewriting the equation as c a equals 1 and finding the value of c, which I can write as c equals 1 over a. That is, the constant probability is inversely proportional to the width of the well, and that's obviously intuitively correct. Longer the width, lesser will be the probability. So the probability is inversely proportional to width of the well. Now, from the theory of probability, we know that the average position of the particle is given by the average x equals integral from 0 to a x times the probability of finding the particle at position x times d of x. And if I substitute the values from equation 4 and equation 5 sequentially, I can write the equation as c times integral from 0 to a x times dx, and applying the integration and putting the value of c, I can write it as 1 over a as value of c times x squared divided by 2 with limits from 0 to a, and substituting the limits, I can write 1 over a times a squared divided by 2, and cancelling the square of a in the numerator with a in denominator, I can write finally it as a divided by 2. So the average value of position is directly proportional to width of the well, and this equation says that every position of the particle within the well for a given width is equally probable, or another way, it is independent of time. Squaring this equation, I can find the square of the average of the position, which obviously goes like x average whole square. X average square is equal to a square divided by 4. Similarly, the average of the square of the position is given by x square. The average of a square equals integral from 0 to a x square times p of x times d of x. And if again I use the value of p of x equal to c and then the value of c, I can solve this integral very easily, which gives me the value like I have shown in each step equal to a square divided by 3. From these two last results, the standard deviation of position is given by delta x equals square root of the average of the square of position minus square of the average of the position, and if I substitute the values, it is straightforward to reduce the results to a divided by square root 12. This equation gives the standard deviation of the position of a particle in infinite potential well from the perspective of classical mechanics. Okay, keep these results in your memory and wait for my next video on the same topic from the perspective of quantum mechanics. From the comparison of two videos, you will understand how the theory of quantum mechanics changes the fate of the particle inside an infinite potential well. Don't forget to stay connected by subscribing to SAFI Mixed.